there's more. It was like final project.
Okay. Any questions on, any lingering questions on Lab 4? I think there's only 3 groups still have to check out today. And, but remember that final projects have started, therefore, and that you will have a weekly progress report necessary, including next week. So you want to get busy on this, and throughout the 5 weeks, you are required to be in your usual scheduled lab section, unless you make some specific arrangement with your TA. So again, any questions about final projects then at this point? I will be I'll be submitting an order on Monday to DigiKey and All Electronics. So get your stuff to me, get your request to me by 8 a.m. Do people think they're going to be working on in the mornings next week? Final project. You gonna? I can. Yeah. So what I'm going to do is what I've done a couple of times before, and that is feel free to. I'll check at 9 a.m. to see if anybody's sitting around waiting to get in the lab. And if nobody's there, I'll go back to my office. But at any time, interrupt me and have me open the lab. I'll be happy to do that. We'll get as many hours as possible. Any request? Maybe a week from now, maybe a little longer, depending. We'll stop having lectures and meet only in lab. And but do you have any requests for specific things that you'd like to hear about? Yes.
Sorry, just for clarification, are we going to be having lab time during our lecture slot?
Yes. Lab will be open at normal lecture time. Yes. Typically, a good time. It's a guaranteed time when people can come to lab and at least ask questions. Yes, Margot.
That means there's going to be 90 people in the lab.
Are you kidding me? Are there going to be 90 people in lab? No. Are there 90 people in here today? Doubtful. There might be 35. It won't be full in lab until the last 2 weeks when it will be packed. Therefore, it's a good idea to get your hours in early. There's also a significant bonus for finishing early. Do you have another question?
It's just like, because what would be the policy if there are too many? Because like for lab sessions, you say you give priority to those who are actually in the lab session.
Policy outside of lab sections is first come. First come, first served. We may, if it gets really packed, we may request that everybody get up and leave for at least 15 minutes every 3 hours. Yeah, flush the air out a little bit, and that gives people a chance to cycle in. In the past, we've also had a phone list written on the board where you could write down your phone number, and as soon as a spot opened up, the TA would call. We could do that. That generally won't be a problem, except the last week. Don't wait till the last week to do your work. In fact, get organized, finish a week early, take your 7-point bonus, and smile. Yes?
This is a topic request, but if you could go over using USB, like registering PIC32 as a USB device. That would be very specific.
Registering the PIC32 as a USB device. HID, mass store,
HID.
HID. I'll try. So you want to treat the PIC as an input device for the PC. I think I know how to do that. I'm not sure I know how to do that. What else?
I guess on the topic request, but does something like wireless make these
Wireless, Bluetooth, well, so there's a bazillion different protocols for wireless, and most of the time you're not going to be writing the protocol. You're going to be sending data to a embedded processor on the transmitter, which is going to handle the protocol for you. Bluetooth is a fairly complicated protocol. And I mean, I could put together a summary of that, but you could probably read the same thing as effectively on Wikipedia. I have never written a Bluetooth protocol, nor do I hope to ever do it. It is a monster. It's probably 10 person years of work. So what you're probably going to do if you use a Bluetooth radio is you're going to get a Bluetooth radio that has a serial interface and submit data to it. Is that what you want to hear about?
Yeah.
Okay, I might be able to do that.
For our project, we require recording someone's voice and then possibly using FFT to analyze it. I know you provided the sample code for FFT, but you already had a setup of a sine table there, and I was wondering how you can implement recording sound from a microphone and then applying FFT to that.
So you can set up there's a couple of ways of getting data in. I can certainly talk about that. But you can sample it at a specific rate using interrupt service routine at 8 kilohertz or so, which is what you need for voice. You'd probably use an interrupt service routine to record the samples. Once you get a block of n samples, then you could do an FFT on it. Typically 256 or 512 points for voice. I think I have that whole code actually running as an example on one of the pages. Although, I mean, what do you want to do with the spectral analysis?
We want to we want to do a speech recognition, and we're primarily just recording letters.
Okay, so FFT might be good, or you might use a log distributed filter bank. It might be more appropriate. But if you're going to use FFT, I would suggest that you look up the so-called MEL transformation, MEL transformation, that takes the output of the FFT and turns it into psychophysically relevant bandwidths. So it's more like what you need for speech recognition. It's a straightforward linear transformation. So Bluetooth and USB. I'll see what I can do on that. So since I tend to do things bottom up, I've been, for the last year or so, been working on protocols that are at a lower level than these high-level protocols, but I'll see what I can do. Again, any questions about the final project logistics? demo times, due dates, budgets. Progress report details you have to ask your TA. TAs are free to ask you anything they want. Now, this is self-limiting because no TA wants to read 100 pages a week. But you have to ask the TA what they want to hear. In fact, you have to ask them whether they want it in writing or verbal. It may not even be in writing. It depends on what the TA wants.
So about next week, so we don't have lab time this week.
Wait a minute, what do you mean you don't have lab time this week?
I mean, my lab time is passed, so where should I know what to submit next week?
Why don't you email your TA? And on Monday, I'll have them all. We'll have this more together. Have TA meetings 8 a.m. on Monday. Great time to meet.
Well, since we have already submitted our project design, so is that okay that we change it a little bit?
You are not bound by your project design. That is for us to determine whether or not you can actually do it or not. But if you're going to change it very much, you certainly want to talk to me or the TA and talk about the trade-offs for changing something. In general, I'd like to hear from all of you, once a week or so about progress. Stop by, say hi, how's it going? If you have any questions, if you want to know what we have in the lab in terms of parts, you might want to talk to me. We have almost any reasonable TTL part. We have quite a bit of CMOS logic. We have N-channel and P-channel power transistors. We have JFETs. We've got various kinds of connectors. So before you build an order, stop by this afternoon and find out what we have in lab. It's faster and easier not to have to order it, often cheaper.
So something like, say, a multiplexer, would that be kind of like cheap enough to not?
A multiplexer? You mean like a 7400 series multiplexer?
Sure.
8-to-1 multiplexer? You just budget that at the cost. It'd probably be on the order of 50 cents. Yeah, you need to budget it, but it's going to be easier to get it from the lab and faster. I have analog multiplexers. I have 8-to-1 analog multiplexers. I've got 555 timers. Everybody know what a 555 timer is? The most used integrated circuit in the entire world. It's a timer. Analog timer. So stop by and poke around a little bit. Ask me what we've got. We've got a random selection of motors that are mostly left over from other projects. Some steppers, some DC, some servo motors, just in a big box. Feel free to paw through the box and take what you can use. Those are not budgeted. Those are surplus. There are some shelves in the lab which are surplus shelves that you can dig through for parts. Before you do that, though, you have to ask me which shelves are actually surplus, because it's not everything. By saying it's not budgeted, it means it does not count towards your budget. That is correct. You don't. If it's more than $20, you buy it. I don't peel 20s off and give it back to you. I have no way of handling money. That'd be interesting. Go up to the department and say, give me a wad of 20s. I need 50 20s. Yeah, that'd go good. Yeah, that'd work. Yes?
So the secondary bonus, is that from the lab section?
I've said that, and it's in the lab write-up. But the rule is that there is a table. All right, I'll get out the table. There is a table in Lab Assignment 5 and since I haven't looked at it recently, I'll have to find it again. There it is. Oh, that's really good. What happened here? Well, let's cycle the connection and see if that helps. The last time this happened, I had to reboot the iPad, but I didn't find that out until after lecture. Did it show anything at all at any time? All right, so I'll reboot this thing. There's a table which gives the number of points per day early. It goes as the square root of the number of days early. So that if you're very, very early, you don't get linear number of points. But around 7 days, you get around 7 points. And I'll have to look at the table, because I fiddled with the table to make it a big enough, still nothing. That's very interesting. I tested it. Oh, okay. Final project. Yeah, that's better. So the bonus is 2 points. It's the round of 2.7 times the floor of the number of days to the 1/2 power. That says we're going to round down. So it has to be a whole day early. 23 hours early is 0. All right? So it's the floor of the number of days to the 1/2 power times 2.7. And if we look at the table, which is probably a better thing to do, we see that 1 day early is worth 3 points. 7 days early looks like 7 points. This is measured from the day, from the end hour of the last lab section that you have. So if you're on Tuesday, you have to be a day before 7:30 in the evening. Furthermore, if you are demoing early, you have to demo while I am here, which means during the day. Because I am going to see every demo. I'll be at all of the labs the last week, so I can see all the demos during the normal lab times. But if you're going to demo early, you have to schedule it with me. So where's the psychological sweet point here? You done the cost-benefit analysis yet? Is that explicit enough for the question? It's 24 hours before the due date, the due hour. Right?
So is the Thanksgiving break coming to these days?
This is calendar days, folks. You won't be able to demo over Thanksgiving break because I won't be here. Where will I be? You come out to my house? Demo? It's okay. Yeah, you might, right? In fact, because you're doing a chicken project, right? Yeah. I have chickens. So that's a possibility. So yes, I probably won't be on camp. I will be on campus on Wednesday before Thanksgiving, and I don't know if Wednesday is a day off this year or not. Is it? Oh, they went for the half day again? Because for years it was a half day, and then they said they were going to go to a full day Wednesday because nobody was here anyway. But I don't know if they did this year or not.
If they ever did.
It starts Wednesday morning. Yeah.
Well, that's what I'm saying. Is it full day or is it 1:30 Wednesday?
It just says Wednesday, Thanksgiving recess.
You spoofing me? No, all right, okay, all right. Oh, it's full day Wednesday. Okay, so I will probably be here Wednesday anyway. If you want to demo on Wednesday, but I won't be here Thursday and Friday.
And on the project website, the final, it said that the projects are ranked and then points are assigned based on ranking.
It is, when you have 50 different projects, all with completely different hypotheses, yes, we're going to rank order them.
And then I'm curious how these points come into it. Is that just after the ranking?
After the ranking, this is added on, flat added on, but it's capped at 100%. Yes? You demo, you're done. You have to believe that you're finished. It's one demo. If you're not ready to demo, don't demo. At the time you demo, part of the demo is a rough draft of the web page. So the documentation has to be done at the same time in rough draft form. Doesn't have to be beautiful, doesn't have to be complete. It has to be a viewable web page. Not a Word document, a web page. You can generate a really ugly web page by doing a save as HTML in Word. And the reason it's ugly is that Microsoft embeds a bazillion special commands into their HTML files, so that when you display it on any browser except IE, half the characters that are displayed are question marks. It is horrible. Nonetheless, people do this every year. And it's up there for decades. And it's still ugly after decades. Any other questions about Final Project? After we stop lecturing, the only way I have of doing any kind of broadcast of the class is by email. And so it becomes particularly important for you to read email. And I know that you get 400 emails a day from Cornell, or something about like that. But you better whitelist anything that has ECE 4760 in the title. So anything else on final projects? Well, let's talk a little bit about physical synthesis of music. I don't have any code for the PIC32 yet for physical synthesis, solving the differential equations directly. So that sounds like a final project, is doing physical synthesis. The old AVR-based homepage, the link is there. I don't know, has anybody actually gone to that page and looked at it? Of course not. Because you can barely even tell it's on the home page. But if you go to the old AVR page, looks a lot like the current page, but the links are somewhat different, and particularly, of course, it's all AVR, Mega 644, 1284 stuff. But in the DSP page, there's some code that runs for doing physical synthesis, and you might want to look at that. But before we look at it, I want to talk about the theory of it a little bit. Oh, maybe I'll play one or two things. I think I got when I tested this earlier today, I had the volume turned up and it was pejorative. But I think it's better now. This page has all kinds of interesting things. Second order IIR filters, CIC filters for doing multi-rate filtering, waveform generation, fast Fourier transform, discrete cosine transform, Walsh transform. It breaks things down, breaks waveforms down into orthogonal square waves. Karplus strong algorithm digital waveguides. So this is physical synthesis. Let me just play you one example of a string, linear string tuned to middle C and plucked with high energy white noise. So that's what we're aiming for. It's a pretty good sound. Sounds pretty plucked string-like. So the question is, how do we do that? And And the short answer is we're going to solve the wave equation. So we're going to solve partial of u with respect to partial of u with respect to x plus the d times the first partial of u with respect to t equal to 1 over c squared times the second partial of u with respect to t squared. This is just F equals ma. This is the acceleration of a small piece of mass on the string. We're modeling the string now as some waveform where this is the displacement u. And there's a small piece of mass we're looking at which has some acceleration. C takes the mass into account. Du dt is a velocity, therefore. It's a vertical velocity of the string. And this is a damping term. So this represents a linear velocity-dependent loss of energy. And this is a force represented by, related to the bending of the string. It's how much difference there is between the right-hand side and the left-hand side of the string at a given point. That should look pretty familiar. You can solve this by finite difference analysis. You could write the finite difference approximation of the second derivative, which is nice because since it's second order, it's centered in space. And this is second order, so it's centered in time. It has some nice mathematical properties. But that's probably too slow for the microcontroller to solve for a reasonable resolution. So what we're going to do instead is to use the fact that for a linear string, there is some function, or for any function, x of c minus c of t is equal to x of t. In other words, a traveling wave, a pulse on a linear string without loss, travels with no change in shape. Who solved that originally? D'Alembert? It's D'Alembert's solution, I think. Anyways, and likewise, a wave traveling in the other direction also acts as a translation. Now, if you have a damping term, as the pulse propagates, it becomes a little smaller, but doesn't change shape. So that says that we can replace the differential equation with a series of, bear with me because we're going to take this through about 3 transformations to go from the differential equation to the final form. But we could say, well, if all that happens is that the wave moves one spot in space, over a small period of time it moves a small distance, let's just represent that piece in space as a register, and then when it moves, we'll shift the wave into the next register. And if there's a little bit of loss, we'll insert a loss term here. And then the next little bit of space will be a loss term and another register. And then when we hit the end of when you hit the end of a string for a string with fixed ends, what happens when a wave hits the end of the string? It reflects and it reverses polarity, right? So the wave coming back then is going to look like this. So at the end of the string, then, we insert a -1 operator. Then we have a register, a loss, a register, a loss, and so on until we get down to this end of the string where we have another -1 operator. And then perhaps an adder here for putting energy in from outside. So we've replaced the differential equation now by a shift operation which works because a traveling wave is a valid solution of this equation. Any questions on that? Now, there's an interesting feature of all of these operators. They're all linear. -1, some fractional loss is a linear operator. -1 is a linear operator. A translation in time is a linear operator. And there's a feature of linear operators that we can make use of here, and that is they commute. You can do them in any order, right? So, in particular, we could take all the register elements and commute them into a long line. We multiply by -1 times -1, we get 1. So we just get rid of that. We then have a loss element, which will be the sum of all the losses around the loop. And then we feed it back. So now we've taken the differential equation, we've taken the traveling wave solution of the differential equation, reduced it to a set of shift registers, commuted those operations so that the registers there's absolutely no operations between the registers, but the output of this is then modified by a loss and fed back in. So we can represent the whole string as a circular buffer whose output is modified before it is fed back in. That's pretty efficient. Don't have to move many elements. We just move 2 pointers for the position in the register we're outputting. And if we treat the loss carefully, then we get a reasonable approximation of the physical system. In the case of a string, what Karplus and Strong found out was that the loss can be really well represented as a one-time step delay added together with the undelayed input, and then a divide by 2. In other words, you take the average of the last 2 samples and feed it back in. So an averaging filter is a low-pass filter, not a very strong low-pass filter, but it is a low-pass filter, and the higher the frequency on the string, the more this filters out the recirculating high frequencies. And remember, you might be doing this several hundred times a second, going around this loop. In fact, you want to go around this loop once for every audio cycle you generate, or once for every string oscillation you generate. So you get stronger filtering at higher frequency, which is exactly the dynamics of a string. The higher harmonics drop out faster. What Karplus and Strong also found was that you could, amazingly, as an initial condition, you could just initialize these registers to random values. If you're doing a physical, if you're physically plucking a string, what does a physical pluck of a string looks like? Well, it's probably you're stretching the string something like that. You're pulling on it at one point and then letting it go. So you're getting some sort of triangle or some sort of sawtooth. And the closer you are to this end, the higher the frequency components that are involved in the drive. But what they decided to do was do the really absurdly random thing and put random numbers into each of the registers, which simulates a very high frequency drive. It's because the Fourier spectrum of a random number sequence is broadband. It's almost uniformly distributed over frequency. So this represents an extremely high energy impulse, narrow impulse into the string, which is what you get off of a very fast pluck. In fact, this is so easy that Karplus and Strong did it in the 1980s on an 8080 processor, 8-bit processor running at 500 kilohertz. So you know you can do it on the PIC-32. Any questions on this? There's a couple of details that we need to go into next time. But one of them is you have a wave circulating around this string as if it is oscillating on the physical string. You're simulating the physical string. The more registers you put in, the longer the string, the lower the tone. Right? A long string is lower frequency than a short string. So you control the frequency by the number of shift steps at a given clock rate. What happens if you need a fractional number of shift steps to tune a given frequency? People want A above middle C to be 440 hertz. What if that comes out to be 30.5 shift register steps necessary to implement? You need to implement a half a shift. Anybody know how to do that? A time delay, a fractional time delay? All-pass filter? Sound familiar? Put a step through an all-pass filter. Makes a phase change but no amplitude dependency. Any case, there's a couple of details. One is tuning. The other is the nature, the exact nature of the loop filter that you put in may depend on the instrument. There may also be an output taken off of here, which goes through an output filter before it is before it becomes a sound. I think I tried that in let's see if I actually put it in here. Oh yeah, this is an example that I tried to make sort of vaguely horn-like or clarinet-like by putting an 800 hertz filter in an 800 hertz high-pass filter in the output and low-pass filter in the feedback. I don't know what that sounds like exactly, but and there's some other examples. Let's drive the input. So I drove the input with a. This is with the white noise drive. So now let's put it. Now let's use a triangle pluck. I have to make sure I don't spoonerism any of these. It's a little bit softer. Not quite as nasty high frequency. Another possibility is to pluck with white noise and then drive the string with a sine wave. Or pluck, or no drive at all, but drive a string tuned to 261 to middle C with a frequency of 205 hertz. What's that sound like? I don't know. So you can spend days diddling with this, and I have. So there are generalizations of this for 2 dimensions. There's no reason why you can't generalize this to a set of 2-dimensional delay elements, although it may be beyond the organizational capability of C. But for 1-dimensional systems, I would say reasonably, you can probably do 30 or 40 strings on the PIC 32 in real time at a sample rate of, say, 10 kilohertz. So you could do quite a substantial amount of simulation if you wanted to do string simulation. Does anybody intend to do that? For 5760, I have people do brute force solution of this as a 2-dimensional partial differential equation for a drum head, where they have to drive a square drum. You don't see many of those in orchestras, but drive a square drum head with a Gaussian drive function and listen to what comes out. So the grade is based on the number of nodes they can actually solve in real time at 44 kilohertz. But that's another course. Any questions on this? Any questions on physical synthesis? I'm going to talk a little bit more on this. Interesting. It's very interesting mathematically. And if you want to find out more than you could possibly read, Google up Julius Smith, Stanford, and or watch some of his videos on YouTube. Very entertaining guy. All right, there will be lectures next week, so I'll see you here.